So I'll talk about symmetry in evolutionary dynamics. And unfortunately, I couldn't be here for Steve's talk, but I'm sure it'll be all different. He probably presented some general theories. And I'll stick with 3 particular examples. So these are case studies from my work where I found that symmetry or breaking of symmetry led to some interesting or unexpected results. The first example will be about a color. And maybe some people in the room have seen this. But the other 2 examples are brand new, and I don't even totally understand them. So maybe you can help me. So the first project was about colors. Symmetry breaking in color, categorization, and communication. So we'll first talk about the space of color perception. And that goes to the previous talk, connected with it very well. So can we order all the colors in one line? And the answer is no. And in order to somehow put an order to them, we need at least a 3D, a 3-dimensional space. So somehow colors live in a 3-dimensional space. But of course, the light that we receive that is reflected through objects, those signals belong to an infinitely dimensional space. This is the spectrum of the light. It's the space of all functions. So somehow we collapsed an infinitely dimensional space of light that we perceive into a 3-dimensional space of color. And this space is like this globe where we have black at the south pole, white in the north pole, colors of the rainbow that go around the equator, and saturation goes in such that all the colors meet in the middle in gray. And one of the reasons why it's 3-dimensional or space is because we have 3 cones. And each type of cones is responsible for its own wavelengths. So kind of red, green, and blue. And somehow the signal that we receive becomes 3-dimensional. So if we take this sphere and take the skin of the sphere, we can make a color map. If we look at this color map, we can identify colors that we can see: red, orange, yellow, green, blue, purple. These are the colors of the rainbow. Okay? And so these 6 colors plus black, gray, white, brown, and pink are what they call basic color terms in the English language. Magenta, turquoise, burnt sienna, and so on are not basic color terms because nobody knows what they are. People disagree, especially men. So they really have no idea. The number of basic color terms, and there is a rigorous definition of basic color terms, which I won't go into. The number of color terms differs from language to language. For example, in Russian, this is 2 colors, синий and голубой, which are basic. So we have a 7-color rainbow. So the number of basic color terms is different in different languages. It could be as large as 12. It could be as small as 2. So here's an example of a language with 3 color terms. When there are 2, it's usually black and white or dark and light. And it doesn't mean that these people don't see all the variety of colors. It's just they categorize them into 2 groups. If there are 3, the third one is usually red, and there are cultures that have 4 colors, 5, and so on. So there are big differences among cultures, but there are also some universal features that are common among languages, and we want to explain those. So one idea is that perhaps color categorization reflects optimal divisions of a perceptual color space. It's just not necessarily clear what are we trying to optimize. So here's an idea of what we could be optimizing. If I ask you to go and bring me an apple of this color, you will not be able to do it because there's an infinite number of colors. But if you bring me that, that's probably OK. And this is not OK, right? It's not the same color. So it is useful to call similar colors the same name. And it's useful to call faraway colors different names. And it's also useful to communicate about colors. So here's a model that we use to kind of try to understand these things. Take the skin of the color solid. And that's 2-dimensional. Now reduce it to 1D. That's just the color circle. Okay? And this is how we present categorization mathematically. It's a table of probabilities. For example, these are words. These are all the different stimuli. And these are probabilities to call this purple, blue, green, and they add up to 1. So we have a probability to call each color each name. these red ones, this says that this color is always called E, so it's deterministic. Okay, so let's suppose we have.
Are those derived empirically? Or
so this is just, this is a way to describe categorization in a model. Okay, so it's a construct.
So this is a model prediction. This probability is model.
No, it's a model assumption.
Empirical.
It's a description of a structure by which you can
That's
talk about either data or a model.
This is a description of a structure that I'll be using to describe how do we represent categorization mathematically. Right. Categorization in this case is your probability to put each of the stimuli in a box. So red, orange, yellow. You give me this color. What am I going to call?
Kind of mathematical function then, a model, right?
It's a model. So it's a mathematical model.
Which model is it?
Coming up. Coming up. So let's suppose we have, it's a game theory type model. Okay, so we're going to have n individuals. At each update, a pair of individuals is picked at random. They play a game, and the one who wins the game teaches his categorization to the other one somehow, or affects the other one's categorization. And each of these agents is equipped with that thing that you were asking me about. So they have a table, which is initialized to be random. So we pick a pair, we give them 2 stimuli, so that's your discrimination game. And we ask them, what do you think this is called? So this guy is going to use his table, toss a coin, and he says, I think they're called A and B. And this guy says, I think they're both called C. So the question is, who wins? Right? So how do we decide who wins in this game? And this is how it's decided. This is the concept of this model. If 2 colors are close together, like these 2 examples, then if you name them the same word, then your game is successful. And if you name them differently, you fail. And if they're far apart, then for success, you should call them different names. So in this case, agent A called them A and B, and agent 2 called them C and C. And you can see that this guy won because he called 2 different stimuli 2 different names. And we can formalize it mathematically. What does it mean to be close or far? We just set a distance of k units apart. And if they're k within the space of k, they're similar. Okay? And now we can define success rate, and we can define our optimization problem. The success rate is we play these games over and over and over. Actually, just 2 people are playing. And what's the probability that, I'm so sorry, 1 person's playing. So this is just for 1 person. 1 person is playing this game. And what's the probability that the game is successful as time goes to infinity? So what is the best categorization that maximizes success in this game of just 1 individual? And then when we put them together, we have a population dynamics. So the optimal categorization is the one that maximizes the probability of success in this particular game. So we can find the optimal categorization structure theoretically. In the simplest case, in more complicated cases, we can do it numerically. So we can study, so here's a simulation. So we start with everybody having kind of like a random categorization. These are stimuli, and this is the probability. These are where they put them, in which bin. And as time goes by, they all develop a unique categorization system, which is kind of very similar among individuals. And it has certain features that can be predicted analytically. So in this color space that is a circle, categories look like this. So this is 1, 2, 3. The optimal categorization system is deterministic. So we never hesitate. We always know which category to put a stimulus in. Categories have equal size, and each is a connected set of chips. And the optimal number of categories is given by this formula that we were able to derive. So why am I talking about this at this conference? The solution is rotationally invariant. So basically, if this is my categorization system that is optimal, then so is this, and so is this, and so is this. It doesn't matter where I draw the border, as long as the sizes are the same and as long as it's deterministic. So we can run a computer simulation of agents meeting each other, talking about color, and coming up with a categorization system. And every time we get a solution, but it's a different one every time. So these are examples of a 4-category, 5-category, and 6-category solution. But where the borders are drawn, it doesn't matter. We have rotational symmetry. So here's an experiment. Let's take a population, run it 1,000,000 times, and record the location of the boundary. If this is 100 chips, we can record where the boundary established in each simulation. So, and you can see that's kind of like a uniform distribution because it's different every time. Here's a wheel of fortune. In Don Sari's talk this morning, he talked about a wheel. I also have a wheel. The experiment is like this. Let's spin a wheel and record which number happens to be at the bottom when the wheel stops. And you will see a uniform distribution because they're all the same. That's in rotational invariance. Okay, so this is the nature of the solution. The population of agents converges to a common, nearly optimal color categorization, and we can predict how many colors there will be, but we don't know where the boundaries are because.
So the boundaries vary from person to person?
No, in the same population, because they communicate with each other, like those two robots. Eventually, they establish a common communication system. So
from culture to culture, the boundaries would.
From computer simulation to computer simulation.
So there is no empirical basis.
So the empirical basis is that even though there's a lot of variety from culture to culture, if a culture, for example, has 4 color categories, the borders are more likely to be similar. There are variations, but they are not all over the place. Okay, so this information exists in what they call World Color Survey. A lot of information, about 110 languages, is recorded. And if we identify all the languages with, for example, 3 color terms, the borders are approximately in the same place. Not in my simulation, because it's rotational invariant. Okay?
But why would the size of the interval be the same?
The size of the interval?
Yeah.
Well, so there are other considerations that are not taken into account here. For example, pragmatic usage of red, right? Maybe it's more important to identify red because it's an edible fruit than green. So this is kind of not there. But I'll show you another way how symmetry is broken. Okay? And
are you saying we invent red?
I'm sorry?
We invent it? Do we invent it?
Yes, we invent it. It doesn't exist. It's just something that we categorize. Okay, so what is the solution of this rotational invariance? What breaks it? And one possible solution, and there may be many more, is the existence of Dichromats. These are people who failed this test, and about 7% of them in a Caucasian population, 7% of males. For them, the color space is squished. So for a normal observer, we have a circle that I already drew. And the dichromats kind of, to them, red looks similar to green. So it gets squished in a certain direction. This is just squished a little bit. Only 2 points are identified with each other. And this is squished completely. So you can imagine different degrees of this color blindness, right? So now let's include dichromats in the simulation. So there's no dichromats. But now we're going to include a variable percentage of dichromats and record the position of the color boundaries. And look at that. So here, boundaries used to be all over the place. Now they're completely fixed and anchored to certain positions. So a small presence of dichromats in the population completely breaks the rotational invariance and anchors the boundaries at a certain place. And going back to my wheel of fortune analogy, let's glue a penny to the wheel. And now repeat this experiment. Just a penny, a very small difference. But now it's always going to be the same number that ends up at the bottom because the rotational symmetry is broken. So a small percentage of these different types of observers that have a different color space breaks the symmetry. So what happens is, so for normal observables, any of these is a good solution. But dichromats, they have a non-ambiguous axis, so they can distinguish blue and yellow very well, and these two are squished, red and green. So these two axes dictate the position of the boundaries. I'll just give you the answer. So axis of non-confusion attracts, and axis of confusion repels color boundaries. And so this way, they're completely fixed in place. Okay, so this is the end of the first example, which has to do with color vision. And my next two examples are completely unrelated, but and they're new, and they have to do with evolutionary biology. So this example is about mutant fixation in a random environment. So I'm completely switching gears here. So let's suppose, so I'm going to start with something abstract, and I'll give you useful applications. Suppose there are n cells in a box, okay? And so we're going to talk about their reproduction and death. At each update, remove one of them at random, and the probability to be removed is the same for all. And then would double another one, one of the remaining ones. What will happen? Okay, so let's suppose I remove this one, and this is chosen, and it reproduces, and the progeny is the same color, right? Okay, so now this one dies, and it's replaced by this one. So it keeps happening. So what will happen eventually? There's only one outcome of this game. What is it? What do you think it is? What's going to happen?
Color fixation.
Exactly. Everybody will. I cheated. I didn't because it takes too long. But so eventually there will be only one color, and there's no other way, right? So which color? It's obvious. It's symmetric, right? They're all the same. So from symmetry, any of the colors is equally likely to dominate. So the probability for orange to dominate is 1 over n, and so is the probability for blue to dominate, and so on. Okay. Now we can talk about evolutionary theory, and maybe we have wild type, like normal cells, and mutants. So I'm going to refer to the orange ones as wild type, and black is mutant. Mutant may be different or the same. So we can assign fitness to these things. So all the normal ones have fitness 1, and the different guy has a fitness R. And the question is the same. What's the probability that the mutant will eventually dominate the population? We assume that the probability of death is the same for all, but the probability of reproduction is weighted with fitness. So if I have I normals and J mutants, then wild type will reproduce with fitness I weighted divided by this, and mutant reproduces with RJ. So it's your probability is skewed if R is not equal to 1. Okay, this is very simple, and the result is well known. The probability for the mutant to take over eventually is given by this formula. For example, if the fitness of mutant is 0, then the probability of its fixation is 0. It will never dominate. If the fitness of mutant goes to infinity, then this function will go to 1. With certainty, it will dominate. And for us, what's important is when R goes to 0, so mutant is the same, then probability of fixation goes to 1 over n. So because everybody is the same, if I start with 1 out of n black cells, the black will dominate with probability 1 over n. Well-known result generalizes to the initial condition where we have I mutants at the beginning. So if the mutant is neutral, the probability of fixation is I over n. Probability of fixation equals to the mutant's initial frequency. Right? So this is a well-known result in genetics. It's I over 2n if reproduction is sexual. This is simpler. It's asexual reproduction. In space, the same thing happens. So if we want to model things in space, we just have different rules of reproduction. If I kill a cell, then not everybody can replace it, but only individuals from nearby. So I draw a box. For example, only these 2 neighbors can replace this guy in a circle, and only these 8 cells in 2D grid can replace the dead cell. Okay. And again, you can prove that the probability of fixation starting for 1 cell for a neutral mutant is 1 over n. Okay. Now, I want to make a modification to this classical problem. This is where new stuff starts. I'm going to make the fitness values random. So for simplicity, I can draw them from only 2 values, 1 plus epsilon and 1 minus epsilon. Okay, only 2 types of fitness. For example, like this. So 1 minus epsilon, 1 minus epsilon, 1 plus epsilon, a random realization. Okay. So this is for wild type cells. So this is a string that I generated from a random distribution for the fitnesses of normal cells. Now, when you're a mutant, I assume that your fitnesses may be different. So to generate the, and they will depend on the spot where you're at, right? So this is fixed. If you're at this spot, your fitness is 1 minus epsilon. But if you're a mutant at this spot, well, here in this random realization is 1 minus epsilon, but it could be different. Like if you're at this spot and you're normal, your fitness is 1 minus epsilon. If you're a mutant, it's 1 plus epsilon. This string is generated again from the same distribution, and the mean is 1. Why am I doing this? And how can this be? So here's one simple illustration of for the motivation of this. Let's suppose we have patches of soil, and there's some plants growing, and the environment is non-uniform. There could be sunny spots, there could be shady spots, and there could be spots with rocks. And we can assume that, for example, wild types hate rocks. They hate them. So wherever there is a rock, the fitness of the wild type will be 1 minus epsilon. And if there is no rock, it's 1 plus epsilon. Okay, but if you're a mutant, maybe you don't care so much about the rocks, but you absolutely need sunshine. So the mutant fitness is now dictated by the sunshine. So it's going to be 1 plus epsilon where there is a sun. You see, so these are different realizations. And they can be correlated, uncorrelated, anti-correlated. The most interesting case is uncorrelated, but we can study them all. So the procedure is like this. We're going to go around the circle, throw around the fitness values for the wild types, then go again randomly throw mutant fitness values, then place a mutant, one mutant at one spot randomly chosen, and calculate the probability of mutant fixation. Now it's not 1 over n, of course, because it could happen by chance that all the mutant values are 1 plus epsilon, and all the normal values are 1 minus epsilon. So there could be some environmental difference that makes the mutant advantageous. Or there could be some environmental difference that makes the mutant disadvantageous with the same probability, right? They're completely, okay. And then I'm going to average over all the realization of random fitness. So this is the procedure. I don't know if I explained it well. This is the first time I'm explaining it to anybody. The environment makes fitness values random. Mutant and normal fitness values are, say, uncorrelated, but they have the same mean, and we average over all the environments. So by doing this, I think there is no advantage to mutants, right? Because their fitness values are the same. Okay, so now I'm going to tell you what happened. So I was working with a student on this problem, and he solved the case n equals 3. And he got very excited. So for n equals 3, it's easy to solve. You can calculate like the probability. So these are all the possible configurations. Red is mutant, so these are all mutants. These are all wild type. If there's a probability to go from this configuration to that, you can calculate the probability of fixation and then average over everything. He was very excited, and he comes to me and says, you know, mutants have an advantage here. They get fixated with probability greater than 1 over 3. And I've been working with these problems for many years, and I think I developed some intuition. So I said, that's impossible. So I went and I did a calculation, and of course the student was wrong. The probability was 1 over 3, nothing interesting. Amazingly, the student went back, and he did the problem for n equals 4. And I just laughed, right? Like, why would you do this? And he comes back and he says, you know, I still get this result, that the probability of mutant fixation is greater than 1 over 4. And amazingly, he was right. So when n is equal to 4, the probability of fixation times 4 is greater than 1. I'm plotting it as a function of epsilon. And this is correct because I checked it. So my intuition was completely thrown off. You can say, oh, it's not a big deal, right? This is 0.004. But still, there is a little bit of a difference. So somehow, if the mutant was neutral, then probability of fixation times n would be equal to 1. And we have a certain deviation. Now, when we do it for other numbers, you can see that the effect is not small. So this is the probability of fixation times n. And in the neutral case, it would be equal to 1, so it would be a flat line. But you can see that, so this is n, the size. The bigger the system size, the bigger the deviation. You can see it's a 30% difference now. And this is the amount of randomness, so how big the fitness differences are. And this is a big difference. And so the effect grows with the amount of randomness. Let's do it for larger n. Now you can see that the effect is huge. Look at that. This is so somehow mutants that are given no initial advantage experience an enormous selective advantage in the random environment. Very puzzling result. So this was done in a circle. And this was done in a complete graph. So actually having only nearest neighbors reproduce into the empty spot is not necessary to obtain this result. This is a complete graph, so anybody can replace anybody else. You can also do it in a 2D geometric network, so you are replaced with your neighbors in 2D. So mutants, without any evolutionary advantage, behave as if they're selected for. Their probability of fixation is significantly larger than 1 over n, and the effect increases with the amount of randomness and with population size. And this only happens if the initial fraction of mutants is a minority, so if they're less than half. If they're more than half, the effect goes the other way around. So I have some feeble attempts to explain it, and I don't know if it's satisfactory, so we're still working on this. So here's my kind of naive way of trying to make peace with this. So we have a formula. Let's talk about the circle. So in a circle, the probability of fixation in a large circle, n goes to infinity, is given by this formula where R is the fitness of a mutant. And this formula, of course, holds in the absence of randomness, right? So now let's take epsilon equals 1/2. So such that fitness values can be 1/2 or 3/2, 1/2 and 3/2. So in the best case scenario for a mutant, all the mutant fitness values are 3/2, and all the wild type fitness values are 1/2. So mutant is completely advantageous. This is the best case scenario. In this case, the probability of fixation is 1/2. You can stick it in this formula and you get 1/2. And now let's look at this configuration. By chance, a mutant, the wild type fitness values, and by 0 I mean smaller fitness, and by 1 I mean larger fitness. So the wild type could be 1 minus epsilon, 1 minus all of these, 1 minus epsilon, just by chance, many spots, k spots on each side. It could happen, right, by chance. In this case, the mutant, if it's placed here, will have a very good chance to win regardless, more or less, of the mutant fitness configuration. So if by chance you have this configuration, you can vary the configuration of mutant fitnesses, and most of the time your probability of fixation is almost 1/2. And the interesting part here is that to create this configuration, this happens with probability 1/2 to the power of 2k plus 1, which is independent on n. So somehow, with the probability independent on the size, you can have this very favorable configuration that makes the mutant, it gives it an initial push. Okay? What happens later doesn't matter. So if the mutant kind of gets off from the initial very high probability to die, that gives it enough of a push to give it an advantage. So this is what this is the best I can come up with. Still working on a better explanation, but I hope there's something there. Why am I doing this problem? I give you 2 applications. One is biofilms. Biofilms are communities of bacteria that have a sedentary lifestyle, so they live in 2 dimensions. And it's a community. It's almost like a society. They have interactions. They communicate. And this problem is very important, for example, for doing antibiotic resistance in bacteria, because they're much more resistant to antibiotics if they happen to be in a biofilm. So the environment in such biofilms is random. I found a large literature just talking about how variable the environment is. There are chemical differences between different spots and physical differences. And there are different mutants, mutant bacteria that live in this environment. And in fact, there is even an insurance hypothesis that states that the more heterogeneity there is in this society of bacteria, the more it's likely it is to survive against the harsh environment. So for us, it's important to understand how fixation happens in such things, because random environment obviously plays a role here. Another application is cancer. So in cancer, a tumor is also very heterogeneous. And there are spots that have more oxygen or less oxygen, more nutrients, less nutrients. There are macrophages and stromal cells that create pockets of higher fitness and lower fitness. And they're made out of non-malignant cells. So I've been working for years on colon cancer. And it happens in crypts inside the colon. This is what a crypt looks like. If you magnify it, it kind of looks like this. And the most important type of cells is stem cells. They are depicted here. But this is a two-dimensional slice. You put it in 3D. I'm sorry, if you put 3D back in, the stem cells now form a circle. So this is kind of like a real-life application of the circular geometry of that problem. And of course, the microenvironment is random. So whenever we calculate the rate of cancer or progression, right, random environment must be taken into account, and it gives a huge correction to whatever we do. Okay, so symmetry breaking somehow happens here, and mutants are advantageous just by the fact that they're minority. Okay, so we can say minority rules. Interestingly, it doesn't work in the same way in the next example. So my last example is infection spread, an invasion of a neutral viral mutant. Okay, so now you're going to see something completely different. So we're going to talk about viruses infecting cells. Let's model infection spread in the presence of multiple infection. There are n cells, and each cell can be infected with 1, 2, 3, up to m copies of virus. Let me just show you a picture. Okay, so there are a bunch of cells. You can infect them with different numbers of copies of a virus, and the process is like this. You pick a cell, and it can send a virus particle to another cell. Okay, and it can add a virus particle to an existing infection. And the other type of event that can happen is death. If a cell dies, it's immediately replaced by a cell that's uninfected. That's all. And this kind of mimics what happens in a tissue where the viral spread occurs. Viruses jump from cell to cell. There can be more numbers of viruses per cell, and they die and are replaced by uninfected cells. Okay. As time goes by, an infection gets established if the probability of infection is greater than the probability of death. And we can calculate the probability distribution of the number of viruses per cell. This is not important here. What is important is now let's talk about two types of viruses. We're going to have a viral mutant. So before I only had black axis, now I have black and white axis. And let's suppose they have exactly the same parameters. So it doesn't matter, they just differ by color. Okay, and I repeat this process. Okay, and the question is, what is the probability that a white viral mutant will dominate in the end? Okay, so if you solve a toy problem with only 2 cells, it turns out that everything depends on the initial condition. If the initial condition is normal virus in this cell, mutant virus in that cell, the probability of mutant dominating is exactly 1/2. This is a function of the function of infectivity. So as expected, half of the time the mutant will win, half of the time the normal virus will win. And by winning, I mean there are some cells that are only infected with mutant virus. Okay, these initial conditions are also symmetric, right? So here, again, half the time the white viruses will win. Now, the symmetry can be broken by the initial condition, and it's not too surprising. So, like if you start with this configuration, you can see that it's not the same. So one mutant, two normal viruses here, and the probability is not equal to 1/3. It kind of goes like this, right? And you can see all sorts of configurations. But the initial condition is asymmetric, so it's OK. I can live with that. But now let's look at this really. Let's increase the number of cells. So with this initial condition, again, half of the time, the mutant virus will win. Now, if you have this initial condition, the symmetry is broken. So how can you figure out what the answer is going to be? So 1/2 of the cells is initially infected by a mutant. So here's 1/2. 1/3 of all viruses are initially mutant. So that's 1/3. So the real thing is kind of in between. So I keep changing the initial condition. It still stays between the two lines, then kind of doesn't. So it's a little bit complicated. But here's what I really wanted to share. Now, if you start with this initial condition, the probability for the mutant virus to dominate is 1/2. Now let's start with this initial condition. So it's completely symmetric. Everybody initially is in the same position. One virus per cell. It's just these two are non-mutant and this one is mutant. You expect 1/3, but it's not 1/3. It changes with infectivity. And this symmetric initial condition also gives you less than 1/4. So in fact, you expect 1/4. But because the mutant is the minority, it loses. The probability of invasion is less than 1/n. So I think I have an explanation. Why is the symmetry broken? So let's look at this initial configuration. I showed you that this is an analytical calculation. The probability of fixation here is less than 1/6. But now if we assume that all the mutants are different, it's equal to 1/6. Why? If you start with this initial condition of when every virus is different, this state classifies as black viruses won, right? And this state classifies as white viruses won the battle. And the probability of this configuration or this is the same. You can see it intuitively from symmetry. But now, if this is your initial configuration where all these are the same, and this is not, this is much more likely than this. So somehow, this is where the symmetry breaking occurs here. So symmetry and symmetry breaking can be responsible for interesting and counterintuitive phenomena in evolution. And they can be important both as funny examples or in useful applications. I would like to thank my group. And if you want to learn about more useful applications, buy these books. Okay, thanks.